Welcome to another Let's Calc video. In this video we're going to focus on the problem set that devotes its attention towards differentiability, both determining whether or not a function possesses that property and at what x values it doesn't, as well as how we can find particular scalar or constant values in order to ensure that a function does possess differentiability. Along the way, we'll look at the major different types of functions that have differentiability issues, what they're called, how to determine them. We'll look at both the how and the why to approach those problems. We'll also look at some extended Fourier response that involve some of these pieces as well. Without further ado, let's jump into the first problem. Alrighty, our first question we're going to attack is question number 2. Question number 1 on the assignment was focused on the visual of that, and I'm hoping that's something that directly comes out of the lecture. If not, you can look at the assignment itself. In questions 2 through, I think it's 9, can't tell. I believe it's questions 2 through 9, you're asked to find all the x values for which a function f is non-differentiable. In other words, we're looking for places where the derivative or the slope doesn't exist or cannot be determined. And our job is to classify each x value appropriately using the nomenclature or names for each of those types of differentiability problems that we might run into. So there are a couple major functions that pop up with differentiability issues. Oftentimes piecewise functions present issues in that world and in that regard, so we'll talk about them when they come up. But the other three major branches of functions that show up are absolute value functions, cube root or odd root functions, as well as rational functions. All of those functions tend to naturally produce some sort of differentiability problems. So as I said in the intro portion, I want to address both the how you can determine where the differentiability issue is and what type based on the type of function you have, but also the why. So each time I'm going to also explain the why, which is not something I do every single time in the written problem set solutions. So you get a little bit of extra work here, and I'll explain to you why all these things work out the way they do. So a couple things to point out too. There are a bunch of different pieces in here. There's a bunch of different things to talk about, but in particular, if a function is differentiable, and yeah, just so you know, when we say differentiable, oftentimes you'll see it abbreviated as diffable, simply for the sake of spelling. It's easy to mess up all those internal E's and R's, but also because it's a little bit quicker to write. So if a function is differentiable, what that tells us, so we could say f is differentiable if and only if. We could say the derivative exists at every x value on that function, but instead I'm going to state it this way. F is differentiable if and only if f prime is continuous. In other words, if our function's derivative is a continuous function, meaning that for every value, the limit and the actual function value on that derivative both are equal to one another. So there can't be any asymptotes, there can't be any holes, there can't be any of those things. So just keeping that in mind, the approach that I'm going to show you in these examples in the video solutions is going to focus on that idea. What we're going to be looking for is to make sure that f prime is a continuous function. Now with that said, I mentioned that there are three major types of functions that have differentiability issues, and those will allow us to quickly diagnose and find that x value just by looking at the type of function. So our first type of function to look at is an absolute value. So if you have an absolute value function, so I'm going to call this y equals f of x, I'm going to say non-differentiable at all x with f of x equal to 0. So, and I should say is potentially non-differentiable. There are some possibilities where it may be differentiable still. In particular, I'm thinking of the absolute value of x squared where the notation is redundant. But for the moment, what we're going to look at is we're going to look as a potential place where this function is non-differentiable by looking for where the argument inside the absolute value markers is actually equal to 0. So in our particular case, as soon as I see that this is an absolute value function, as in it's transforming anything that's positive, or it's keeping positive things positive and transforming negative portions of the function to positive. As soon as I see that, that tells me that we're going to have a point of interest wherever the argument, which in our particular case is 2x minus 7, is equal to 0. Now that can quickly solve for us into x equals 7 over 2, or 3.5. 3.5. And in particular, at x equals 7 over 2 on absolute value functions, we have what we call a sharp turn. Now, there are lots of other names that are used for this. You sometimes will hear cusp. You'll hear lots of different things, corners. I think one year people called it a pointy point. Lots of different ways to go here, but absolute value functions typically have sharp turns. And a sharp turn, I'll remind you, and this is just kind of becoming our little vocab glossary here. A sharp turn is where f is continuous, but the two left-hand limits do not equal one another. So the limit as x approaches c from the left side of f prime of x does not equal the limit as x approaches c from the right side of f prime of x. And now if we picture what absolute value functions look like, it should make sense that this is absolutely true. Haha, absolutely true. Don't you value my contributions? So there's an absolute value function. Of course, it forms a v, and you'll notice that the slope on this side is negative, whereas the slope on this side is positive. There's no soft landing like there would be in a quadratic, where it literally changes to 0, goes through all the negative values, goes to 0, and then goes positive again. In this case, it just literally goes from negative to positive on the other side. So this means that we have what we call a sharp turn. Now I said though that I wanted to explain to you why it is that this works. Like in a sense, what I just showed you is kind of the how to do it, how to approach an absolute value function and focus on it. But instead, let's think about the why. So I said that if a function is to be differentiable, its derivative needs to be continuous. Now you might or might not know the derivative for an absolute value of a function. It's actually not impossible to do, but we typically address it just because it's a minor thing in Calc Prep. But for the moment, what we can do is we can think about the function that's represented by absolute value of 2x minus 7. So this is a piecewise function. We know from just kind of thinking about how absolute values are is that they're centered at the place that makes the inside 0. So that means for x values less than 7 over 2, we're going to have, the negative of the function. And again, you should have done this in pre-cal at some point. And for x values bigger, and I'm just going to put the or equal to right there, we should have the positive version. And again, you could feel free to graph this and check this out, but this is absolutely true. In a sense, if you picture what this absolute value function looks like, it is the line 2x minus 7. What's happened, though, is at that point where it was equal to 0, the bottom part has been reflected upwards. In other words, we multiplied it by a negative in order to make sure it stayed positive. So just kind of an interesting thing. So now that doesn't really help us, though, because we're interested in the derivative itself. So with that in mind, though, what I'm going to do is first I'm going to distribute in that negative. So we talked about where it came from. So this is really negative 2x plus 7. The other one's 2x minus 7. If we want to compute the derivative of this function, which is the derivative of absolute value of 2x minus 7, we can just differentiate the piecewise function. We've done this many times before. The derivative of negative 2x plus 7 is negative 2 when x is less than 7 over 2. And the derivative of absolute value of 2x minus 7 is just going to be positive 2 when x is larger, with potential issues in the middle. And what you'll notice is our derivative, imagine graphing that derivative for a second. This derivative is negative. Oops, don't know how to draw things. It's negative, and then it's positive. Literally, if this is f prime is not continuous. So what you're seeing is you could also determine where the function is discontinuous if you compute its derivative and find anything that makes that function, or that derivative function, discontinuous as well. So for our purposes, we don't have to go that far. It's perfectly acceptable for you to figure it out just by looking at the type of function and knowing how to find it. But it's nice to kind of remind you why it is that this actually works out this way. That there is a reason, and we can see, based on one definition of differentiability, that since the derivative is non-continuous or discontinuous, means that this function is non-differentiable. So there is our first type of function, and there's our first approach at looking at a function's differentiability. Okay, the next function type we're going to look at is this one, which is represented in number 3. You'll notice that I chose 2, 3, and 4, the first ones, to focus on one of each kind. And this is a cube root function, also known as an odd root function. Odd root functions also have a built-in issue. So in an odd root, let's see, how did I do this last time? That's right. So if y is equal to an odd root of f of x, then there's going to be what we call a vertical tangent where f of x equals 0. So, and of course, if you picture what a cube root function looks like, just kind of going along with it, cube root function looks just like a cubic, except in the middle, and this is just the parent graph cube root of x, by the way, in the middle there's a place where if you drew the tangent line, the slope gets super vertical. It basically goes to infinity for a moment. And so this is what we call a vertical tangent. It's another situation like the sharp turn, where the function is continuous. In other words, every x value is fine in there, and they all can be connected nicely and smoothly, but the derivative is not continuous. So now, of course, how do we do that? We said we'd do that here. For our particular case, if we want to find where the function f of x equals cube root of 3x plus 12 is non-differentiable, we take the argument of the function, and we set it equal to 0. Now, clearly, that's going to occur when x equals negative 4. So we can say for this function, because it's a cube root, and we know how to diagnose that issue, we have a non-differentiable point at x equals negative 4. In particular, the reason is that we have a vertical tangent. And be careful that you don't write vertical asymptote by mistake. We are literally talking about a vertical tangent line, a place where if we drew the graph to the point on the curve, we would literally be going straight up in the air. That's what we're talking about here. So there is our answer. Now, once again, though, just because we've explained to you how to find it doesn't mean that that necessarily sticks. It's good to explain to you why. So you just saw the how. Here's the reason why. Look at f of x once again. We know that we're supposed to have the derivative be a continuous function. So if f of x is the cube root of 3x plus 12, also known as 3x plus 12 to the 1/3 power, then we can look at f prime of x's behavior to determine some information about whether or not this guy is differentiable. So f prime of x in this case, it would be requiring the chain rule, by the way. Don't let me fool you there. This would require the chain rule. This would end up being 1/3 u to the negative 2/3 times the derivative of u. And again, you got to plug back in whatever that original thing was. Just doing the kind of fast chain rule here for the sake of time. That makes this entire thing, well, since 3x plus 12's derivative is 3, those guys divide away, and we're left with 1 over 3x plus 12 to the 2/3 power. So now this function, if we look at its behavior, the numerator is never 0, so that's nice, that's cool to know. But the denominator, at x equals negative 4, if we were to evaluate at x equals negative 4, then that would imply that we got 1 over negative 12 plus 12 to the 2/3 power, which is 1 over 0. And that we know is either infinity or undefined. So the reason I bring this up is, once again, if we look at the derivative of the function, we can literally quickly diagnose whether or not there's a place where there might be something different, non-differentiable. And as soon as we found a 0 in the denominator, that meant we had a point that didn't exist on the derivative, which meant, of course, we have a function with a vertical tangent in this case. So once again, the derivative kind of explains the reasoning that otherwise you might just kind of commit to memory. But it's nice to know why exactly this one works. So there you go. There is our odd root situation shown for you. Okay, the next function type that we're going to look at and analyze a little bit is what's represented in question number 4. This one is a pure rational function. We have f of x equals x squared minus 1 over x squared minus 5x plus 4. So the last thing that we have to look at here is the other way you could have a function be non-differentiable is just at any discontinuity. Let's see, let's do this. I'm going to write this better. What the heck? Discontinuity at x equals c? What that means is that our function is non-differentiable at x equals c. So in other words, if we have a vertical asymptote, if we have a hole, or if we have a jump, our function is not differentiable at that point. And that should make sense. Like trying to think about how you could draw a tangent line to a point that doesn't exist. It's going to be hard. There's no point in tangency. Trying to think about how you could draw a tangent line to a vertical asymptote. You can't, because literally we would have to start at infinity, and it's kind of hard to get there. And how we would have a vertical asymptote if we had a jump, well, which side would you put it on? And that wouldn't necessarily be accurate. We wouldn't be able to approach it from both sides, as the definition of the derivative requires. So in this case, as we look at our function, it's simple enough just to analyze it like we would if we were looking for vertical asymptotes or jumps or holes, or any just kind of discontinuity. So doing some quick work here, we can factor the numerator into x plus 1, x minus 1. Our denominator looks to me like it factors into x minus 4, x minus 1. So what I see is that the x minus 1's divide away, and we're left with, not equal, but it's left with, it's a function that agrees everywhere except at one point, x equals 1. We'd be left with the kind of cleaner function, x plus 1 over x minus 4. So with that in place, this gives us two pieces of information. There is a hole at x equals 1. There is also a vertical asymptote at x equals 4. And if you'll recall, there's holes wherever the factor divides away, because of course that produces 0 over 0 that we can divide out and get taken care of in the limit. And there's a vertical asymptote at x equals 4, because it makes the denominator of the function 0, and the numerator not, which means that as you approach from one side or the other, the function will go to plus or minus infinity. So with that in mind, collectively, that tells us is that we have a discontinuity, at x equals 1 and 4. So the function is non-differentiable there, and our reason would be discontinuity. Discontinuity does preclude differentiability. So with that said, this is the other kind. I would go through and compute the derivative for you, and you'd be able to see that those things were there, but this would, I don't really want to do that right now. So forgive me for not going through and differentiating that massive chain rule thing. Trust me, though, it does actually work the way I expect it to. And in fact, you'll end up with a hole on that thing, as well as an actual vertical asymptote, of course. Okay, that brings us to question number 7. 7 is a step up in difficulty, I would argue. It was one that I came up with as I was rewriting the problem set, but I think it does a good job of helping you diagnose the sorts of things that are here, while also recalling something that's fairly useful, nonetheless. So our function f of x in here contains a lot of issues. So we've got 5x minus 45 in absolute values. When I see absolute values, that makes me think of issues. I might have some sort of sharp turn, maybe there's something else going on. And then the denominator, I see that there are at least 2 values. There are definitely 2 values that make the denominator 0. So I know for sure there's going to be a few issues revolving around plus or minus 9. For the moment, though, what I want to do is I want to recompose this function a little bit. I want to make this a little bit different formed, so that way we can analyze it a little bit differently too. So my numerator, I'm going to factor out of 5. And that's okay, of course. Imagine if you didn't want to, that you just distributed it back. You'd see this would be equivalent, because we pulled out a positive 5. In our denominator, that is a difference of squares that factors to x plus 9, x minus 9. So although this is purely, speculative, the way I'm going to write this function is as 5 over x plus 9 times absolute value of x minus 9 over x minus 9. And this is an interesting function. I cannot lie to you. So what I'm looking at here is I see 2 different types of behavior. I've got 5 over x plus 9, and there's nothing in the numerator that's canceling an x plus 9, so that makes me fairly sure that there's a vertical asymptote at x equals negative 9. I don't think we have any issues. I don't think there's any issue or anyone that distrusts me there. And if you graph out this function, you'll notice that absolutely there's a vertical asymptote right there. So we know there's one point that's going to be non-differentiable, because of course a discontinuity means that your function is non-differentiable also. The other issue, though, is this guy on the side, the absolute value of x minus 9 over x minus 9. Now, this is not a new beast for us. We have run into this type of function before. And if you'll recall, in fact, let's just imagine, it's been a little while, but if you'll recall, the function absolute value of x over x is actually going to appear to be what I typically call the natural jump. When x values are positive, this is positive 1. When x values are negative, this is negative 1. And if you think about why, you can imagine the definition of the function itself. Absolute value of x is equal to negative x when x is less than 0, and positive x when x is greater than 0, not to mention or equal to, but set that aside for the moment. That means if we divide by x on both sides, we have to divide every piece by x, and you can see we get negative 1 and positive 1. So what that means is that this one behaves differently. I mean, there's definitely a discontinuity there, don't get me wrong, but this one doesn't actually factor out and create a hole. In fact, this is just the natural jump again. And there is, in fact, in this function, a jump at x equals 9. In any case, though, the important thing for us to realize, and you could even get away with saying this without even knowing that there's a jump there, is that there are discontinuities at x equals negative 9 and x equals 9. So just like before, there are 2 places where this function is non-differentiable. And like our previous problem, both of them actually turn out to be discontinuities. So, there you go. Okay, that brings us to our next question, which is a nice segue out of the typical types of functions we've seen. This is a piecewise function. But once again, we're going to be asked to find all the x values where this graph or this function is non-differentiable and to classify each one appropriately. So to start with here, as I approach a piecewise function, there are some unique things built into it. In this case, because it's piecewise, we have multiple different behaviors for the function that are all being combined and only working on a particular interval. So where I start with is I ask myself to analyze the differentiability of each branch. So in other words, what my first question is going to be is each branch differentiable? And again, my thought process here is that if there's any part of a particular function that makes up part of the function, or if there's any differentiability issues built into one of those two branches on the domain in which they're defined, then I can automatically lock that in. I don't have to do any fancy advanced work to figure that portion out. So what I mean is, let's look at the two functions. We have two different branches here to look at. The branch on the right is x squared minus 10, and that is a polynomial, which means that there are no differentiability issues. So actually we're perfectly good. X squared minus 10's portion is totally differentiable. The other one, though, is 24 over x. In fact, I'm going to move this up here. Sorry. Versus. So 24 over x. 24 over x has a vertical asymptote at x equals 0. And now, of course, before I go forward and talk about it, if I look, 0 is less than or equal to 4, which tells me right off the bat that, in fact, there is one value for which the top branch, or the left branch, is actually non-differentiable. So we can say right now that there is a discontinuity, one of the disqualifying differentiability offenses. In particular, as we said, that is a vertical asymptote at x equals 0. So right off the bat, we have 1. We didn't have to do any sort of fancy analysis with the piecewise function. All we had to do was look at each of the two behaviors that govern it and decide if they were differentiable. So it turns out there's one place where they're not. Now that we have it, the next thing we need to look at is we need to look at the boundary. So we need to next ask ourselves if the function is differentiable at the boundary, because that's the other place where a piecewise function, could be non-differentiable. It could be that either of those pieces is fine, but the boundary itself might be a problem. So what we do is we need to check two things here. We need to check first to make sure the function is continuous at the boundary, and then second, we need to check to make sure it's actually got the correct slopes matching up at the boundary. In other words, is it both continuous and differentiable? Knowing, of course, that if it's not differentiable, or if it's not continuous, it can't be differentiable. So let's start with the first property. So in our case, our boundary is x equals 4. So we're going to ask ourselves, is the function continuous at x equals 4? That is our first task. Now, of course, continuity requires 3 steps in that definition. We know those steps. It's basically, in our case, f of 4. The second step would be the limit as x goes to 4. And then the third step would be the two things being equal to one another. So with that in mind, we typically would want to show all 3 of those steps are true, but we don't actually have to here because of how simple the function is. Just looking, for instance, at this thing, f of 4, we can find very quickly on our function. It's just 24 over 4 is 6. So in a sense, knowing f of 4, it's just automatically there. It's included in here because x equals 4 as a part of the function. So that's less the issue. The bigger issue is right here. This is the one we're going to focus our attention on, step 2. So we want to check that the limit as x goes to 4 of f of x exists. So in order to do that, we need to make sure that the limit exists at all. In other words, we need to make sure that the limit as x approaches 4 from the left side of f of x is equal to the limit as x approaches 4 from the right side of f of x. So now keep in mind that does not mean that continuity is only determined by left-hand limit equals right-hand limit. It's just that that's the only part that could potentially pose a problem for us. So that's where I'm focusing. With that in mind, let's actually check this. Let's see if this property holds, see if it's continuous. So as x approaches 4 from the left side, we'd be on the rational. So we'd have 24 over 4. And on the other side, we'd take the limit as x approaches 4 from the right side. That would be 4 squared minus 10. That gives us 6 and 6. Those two are equal to one another, so that means that the limit does exist. And we could easily follow the pattern and show that this means that the function is continuous at 4. So yes, f is continuous. And specifically, I should say at x equals 4. In fact, I'll write that right down here. At x equals 4. So that's a good start. That means we don't have a discontinuity at the boundary, which is a pretty powerful and important thing to know. Our next step, though, is the other thing we need to check. Now that we know the function's continuous, we need to make sure that there's not a sharp turn. In a sense, the second step is checking for a sharp turn. But more than that, what we want to check is that the derivative, f prime of x, is also continuous. Because if it's not, that would indicate that the derivative is not continuous, and combined with the fact that the function itself is, that would tell us we have a sharp turn. So the next thing we're going to ask is f prime continuous at x equals 4? It's an important question for us to figure out. So there are a couple things that are relevant here. First and foremost, we need to know what f prime of x is. So we're going to compute it. Remember, for a piecewise function, our job is to just take the derivatives and evaluate. We'll leave the boundary itself alone, though. So the derivative of 24 over x, that's the same thing as 24x to the negative 1. I'm trusting that you can calculate that as negative 24 over x squared pretty quickly. And that will be for x values less than 4. On the flip side, the derivative of x squared minus 10, yeah, it's nice. 2x when x is greater than 4. And again, I leave out the or equal to because we don't know what's actually happening there. So there's our derivative. Our next question is we want it to be continuous. Following the exact same process as before, I'm going to focus on the limit part. So we want to make sure that the limit as x approaches 4 from the left side of f prime of x is going to equal the limit as x approaches 4 from the right side of f prime of x. So in a sense right here, we're asking the question, is that true? So as we approach 4 from the left side, we'd be on the rational part. We'd have negative 24 over 4 squared. On the other side, we'd have 2 times 4. So on the right side, we have 8. On the left side, we have negative 24 over 16. And you know what? I'm pretty confident those two are not equal. What that tells us is because the function f is continuous at x equals 4, but f prime is discontinuous. In fact, I could even write that in here. F prime is discontinuous. What that tells us is that we have a sharp turn, or a corner, or a cusp, or a pointy point. We have a sharp turn at x equals 4. And our evidence is all that work that we did right above. So in anything, or with any, it's not the easiest thing to find, I'll admit that, but basically what we were doing is we were checking to make sure that, of course, the points came together, and then we were looking to see if they came together smoothly. Otherwise, what happens is we have that like jutting out point, and that is, of course, what we call a sharp turn. So there's question number 8, a really common one to ask you to check. I think in the past few years I've used this as a true or false type question as well. So in any event, there it is. Hopefully that's clarified some things. Okay, our next question is question number 10. And question number 10 modifies and moves forward from the work that we've been doing so far. This one asks us to now get a little problem solving with it, not just verify properties or check properties. So in question number 10, and I think 10 and 11, I don't know for sure off the top of my head, but on question number 10 and I think 11, you are given a piecewise function with 2 extra variables in there. Scalars or constants, a and b. I think in this case they're both a and b. And you're asked to determine what values of a and b, if any, can make each function g a differentiable function. So in this case, we're going to do basically the same work that we did on the previous problem. The difference is, in this case, we're going to actually have to come up with a system of equations that will allow us to solve and work through everything. So let's put this in place. So we want g to be differentiable. And if we want g to be differentiable, what that tells us is that we need g to be continuous. Actually, let's put it this way. We need both g and g prime to be continuous. Fair enough, right? We just want the derivative to be as continuous as the original function. So that's what we're going to do. We're going to check each one. So first, we check g continuous. I want to say the continuity of g, but that sounds like a low-grade sci-fi novel. So let's set that aside. So g continuity question mark will be where we start. So of course, as we said on the previous one, we're not going to have to write it every time. There are 3 steps to the definition of continuity, but we're going to focus on the one that's most relevant to a 2-branch piecewise function like this guy. We're going to evaluate the limit as x approaches 3 from the left side of g of x, and we're going to see if it equals the limit as x approaches 3 from the right side of g of x. So in a sense, that's a question right now. So looking up at our function, we're going to be plugging in 3 in each case. First one will be 3 cubed plus 4 times 3 minus 2. That's going to simplify to 27 plus 12 minus 2, which is 37. And down below, if we plug in 3, we're plugging in 3 for x, keep in mind. We're going to get a times 3 plus b. Forgive me for using capital B's, I just prefer them. I can do it. Yeah, it just looks so bad, whatever. And that's going to be 3a plus b. So keep in mind here, now that we have the stuff ready, what we need to be true is we need these 2 things to be equivalent. So in a sense, we've found our first equation. we need 3a plus b to be equal to 37. Otherwise, it's impossible for this function to be differentiable because the function would be non-continuous. So there's our first move. We found our first piece. I'll even put a little star here just to remind ourselves where we were. Next, we're going to ask ourselves the second question, which is, what about g prime? Does the derivative potentially match up? Or better yet, in this case, what would we need for the derivatives to match up? So now we're going to ask about g's continuity. G continuity? So let's see. In this case, what we're going to want, and again, not using the full definition of continuous, we're just using the cleanest, fastest part, or the easiest place to disqualify and check this. We are going to determine whether or not left-hand limit of g prime equals right-hand limit of g prime. So in order to do that, it would be helpful to have g prime of x. And again, keeping in mind we're differentiating with respect to x, sometimes that can kind of throw people. The derivative of x cubed plus 4x minus 2 is just 3x squared plus 4 when x is less than 3. Again, ignoring the or equal to for now. And then the derivative of ax plus b, that's just a line when we differentiate with respect to x, which means the derivative of ax plus b is just a when x is greater than 3. So with that in mind, we can now plug in everything. So what we need here is we need 3 times 3 squared plus 4. And then the other side, we're just going to have a, because we're plugging in 3 for x, keep in mind, not for a. That's going to be 27 plus 4 is 31. And we need 31 to equal a. Hey, look at that. 31 equals a. That was an awfully generous gift, wasn't it? Cool. Cool, cool, cool. So we found a. It turns out the only way this can possibly be continuous is if a is 31. And that should make sense, right? If we're attaching a line to some cubic, the slope needs to match at that boundary point. Otherwise, it couldn't possibly be smooth in the way that we want it to. But of course, now that we have a equals 31, here's the joy. We can take that value and plug it in to our second equation. In a sense, what we're doing is we're solving a linear system. It's a pretty easy linear system to solve. So in this case, we're going to 37 equals 3 times 31 plus b. So in other words, we're going to get that b equals 37 minus 93. And geez, I don't want to do this, whatever. I think it's negative 56, but let me make sure. 93 minus 37, good old-fashioned arithmetic. 5, 6, yep. So we're going to get negative 56 as b. And there is the second value that we need in order to make this puppy differentiable. So again, if there's anything to take out of here, obviously there's a lot of stuff being done, but I think this organizes the work pretty well. You're doing the same operation twice, just with 2 different functions. We're trying to check to make sure that a function is differentiable and determine what required conditions we have upon the variables in there. So to do that, we first check that it's continuous to make sure the function doesn't have a discontinuity at the boundary point. And then second, we check that the derivative is continuous to make sure we don't have a sharp turn and that everything is nice and smooth so that everything will work out the way we want it to. And there it is. Really common question. You can all but guarantee that one of these will be on your exam. Alrighty. That brings us next to the true or false section. I'm only doing one of the two. I think the written solutions will do a good job on question number 12. But in this section, as it says before, we're going to determine whether the statement is true or false, and then we're going to explain our reasoning. I'm going to keep in mind, and I'm going to remind you, that the key word when doing these things is counterexample. Not as in an example that's sitting on that place where you put your pots and pans when you're done with them or cooking. We're talking about some... Did you get that joke? It's an example that's on the counter. Anyway, we're looking for a counterexample, something that might disprove this statement. Because if we can disprove it even one time, the statement must be false, because there's a situation, either in this case a function or a property, that guarantees it's not always true. So in statement 13, it says, if f of x is a polynomial of degree n, then it looks like dny over dxn, so that would be the nth derivative of y with respect to x is equal to 0. So this is a tough one. There's no way for us to check every single polynomial of every single degree, because that would take us forever. It would never happen. We'd never finish. And it's a nice problem. It's a great question. Pat on the back for me. I don't want to spend the rest of my existence dealing with it. So what we want to think about is if there's a way we can find a potential counterexample. And so in this case, I don't know for sure if it's going to be a counterexample, but I'm just going to commit to a polynomial with a degree that I'm going to define, and then I'm going to check what the nth derivative of it is equal to. Because if it's equal to 0, then we got to do some more work. But if it's not equal to 0, then we would be done. So let's take case in point. Let's let n equal 3 So I'm just choosing one. Again, I don't know whether this is true or false. We're keeping both options open right now. We're just kind of exploring, and hopefully it disproves everything. So I'm going to let n equal 3, so that means we have a third degree polynomial. And then I'm going to let f of x be the third degree polynomial x cubed. Right, that's a third degree polynomial. Everything works. We've set up the beginning part. I think it's called the antecedent. But we've set up the beginning part of this statement. So our question is then, what is the nth derivative? So in our case, what is the third derivative of this particular function? So let's check. So the first derivative, which we'd call f prime of x, sometimes we'd just call dy dx, that's going to be equal to 3x squared. Okay, nothing helpful yet. The second derivative, which we typically call d2y over dx squared, would be equal to f double prime of x, and that'd just be the derivative of 3x squared, which is 6x. Last but not least, we were interested in the third derivative because that third derivative matches the third degree of the polynomial. So in other words, we want to know what is f triple prime of x equal to, and the derivative of 6x is equal to 6. Aha! Elementary, my dear Watson. 6 and 0 are different numbers. What that tells us is we just chose a polynomial of degree n, and we'll just say 3, and the third derivative, is not equal to 0. What that tells you is that this statement is false. So this isn't true. The first function we checked made it false. And now if you're really clever and you want to kind of follow this pattern and you're trying to experiment, you could have started even smaller. You could have chosen a polynomial of degree n equals 1, and then the derivative of that first degree thing would have also not been 0. Case in point, if we let f of x instead equal x, then the first derivative, dy dx, is equal to 1, which is also not equal to 0. So there was even a faster path for us to get there. So in fact, this statement is definitely false. We're done. We found a counterexample. Took a little bit of construction, but we did find a counterexample. But I will point out to you, as I think I do in the written solutions, that if you'd wanted to make this statement true, what you could change is this. Is the nth derivative of an n degree polynomial is not equal to 0, it's equal to a constant. And what that constant is, of course, depends on a lot of different pieces and features of that polynomial. But just know that it's not 0, it would actually be a constant. But that wasn't what the question asked, so we don't have to do anything with it. Just know that that is the truth of the statement in case you were looking for it. Alrighty, finally, this brings us to question 14. 14 is the massive free response, or AP free response style question I came up with. It wasn't a perfect question because I end up using a particular value on the table a lot, but it's who I am. So in here, it says, consider the differentiable function v of x. Values of v of x are given in the table below. Then we're asked to evaluate some stuff. So that's what we're going to attack here. What's happening with this function? So first and foremost, in question 14a, we are told to evaluate the limit as x goes to 2 of 5v of x squared minus 5v of 4 all over x minus 2. So as I look at this expression, I can't help but think of the limit as x goes to c of f of x minus f of c all over x minus c. And I'll remind you that that's equal to f prime of c. The reason I bring this up is in looking at this expression over here, the one we're supposed to evaluate, we can make many similar connections. For instance, I can say that the function f of x that we're differentiating up here is going to be the one that comes right there in our difference quotient. So it looks to me like f of x is 5v of x squared. And then second, because this is the limit as x goes to 2, and x minus 2 is in the denominator, it looks to me like we're trying to calculate f prime of 2. So that's our work. That's what we have cut out for us. So I found the function. I found what we're trying to evaluate it for. So let's attack. So now, if we want to actually differentiate and figure out what the derivative of 5v of x squared is, technically that's going to require the chain rule. And I'm hoping that you're getting faster and faster with the chain rule now that you've had a couple days to let it sink in. But for the moment, let's play it safe. So we want to take the derivative using the chain rule. So we'll use f of u, and we'll use u. So looking at our piece, I'm going to let the inside be equal to u. Looks to me like x squared is the inside. We'll at least give that a shot. That means that our f of u would be 5v of u. And that looks good. I can differentiate that. So now we'll take the derivative of each component, or each factor. We're going to get 5 5v prime of u. And then over on the other side, we're going to get u prime equals 2x. Bringing those pieces together for us to get f prime of x, we're going to get 5v prime of u times 2x, which is going to be equal to 5 times 2x, or 10x, times v prime of u, but u is equal to x squared, so it'll be v prime of x squared. So there is our derivative. Very, very helpful for us to get. The last thing we need to do, though, is not just stop at the derivative. We want to figure out what the derivative is equal to at x equals 2. Again, this is equal to f prime of c, so we need to figure out specifically what is f prime of c. So in our case, c is 2, so we want to figure out what is 10 times 2 times v prime of 2 squared. Looking at our ingredients here, that's going to be 20 v prime of 4. So we ask ourselves now, is v prime of 4 on the table? There's 4. There's v prime. This is 20 times negative 7, which is equal to negative 140. So awfully large negative slope, but who am I to say? I just make the rules. Or I just apply the rules and write questions with them. So in any event, there it is. We use the definition of the derivative first. Then we invoke the chain rule because we saw there was a function inside of another function. That x squared inside the parentheses or inside the argument of v of x was what made us do there. We used the chain rule, and then we eventually plugged in the x value in question to get our slope. So voila. Definitely a challenging question. Don't get me wrong. This is definitely a challenging question, but it's one that I think you should be prepared to approach. Alrighty, that brings us to question 14b. 14b asks, is there a value of c between negative 2 and 1 such that v of c equals negative 5? And then we are instructed to explain our reasoning. So in here, they're asking about a particular function value, whether or not we can get a particular function value. So what this leads my mind to think of is the intermediate value theorem. Anytime you're asked about a function value and you're given some information about what x values to look between, that makes me think of IVT. We're trying to check if there's any sort of conditions that will guarantee that if we go from here to here, the value we want is somewhere in the middle. So in order to do that, remember there are two properties that are required for the IVT. One is continuity. You gotta have a continuous function or else it's not gonna work, or it can't be guaranteed. And then second, we need to have boundedness. So we need to make sure the y value of interest is between the two y values on the endpoints. So we're going to check each of these properties. So in this case, this is consider this kind of my exploration here before I write. I'd love to save a little bit of time as I work forward. So this is me thinking. This is my brain. My brain is for some reason very, very long and wide and strange and purple. But who knows? I don't know. I don't want to cut in my head. So I'm looking here. First thing I want to check, is it continuous? Well, what we're told in the beginning is that we have a differentiable function v of x. So as a reminder, if a function is differentiable, that means that v is continuous. Literally, differentiability implies continuity. And again, you've got textbooks if you want to look up the proof of that and just kind of see why it is that it's true. It has a lot to do with the definition of derivative. So v being differentiable guarantees us that v is continuous. So yes, our function v of x is continuous. Boundedness, our question is what happens at the endpoints. So we need to consider what v of negative 2 is equal to. We want to consider what v of 1 is equal to. So in looking at our table, v of negative 2 is negative 9. And v of 1 is negative 1. So from there, what I know is that negative 5, the value we were interested in, is definitely between negative 9 and negative 1. So at this point, we've seen that boundedness is also guaranteed. So that means, yes, there's going to be such a value in there. All that's left is for us to state it properly. So let's do that. So in here, we have to kind of note all these pieces. And again, I'm going to be extremely careful as I write the solution out to make sure that you don't miss anything potentially on an AP problem. So in here, we want to state that v is continuous. We've already noted that v's differentiability implies v is continuous, but just to be safe, I'm going to start by mentioning differentiability. Since v is differentiable, v is also continuous. So that guarantees our first step. And since v is differentiable, that sounds okay. Since v is differentiable, v is also continuous. And as v of negative 2 is less than negative 5 is less than v of 1. So in other words, we state our boundedness. We also state the continuity part. We can then invoke the intermediate value theorem. So by the IVT, v of c equals negative 5 for some value c in the interval from negative 2 to 1. And this is the answer. Something that is equivalent to this and stated pretty nicely is what I'm looking for as your, the explanation of your reasoning. So again, it's hard to sometimes recognize the intermediate value theorem, especially later when we also add in something called the mean value theorem. But keep in mind the things that kind of lead you there. We're talking about intervals. We're talking about y values. We use what we're given. And I'd say something that's really small. You might not think it's important, but actually a huge thing in this particular problem is your ability to remember to state v is differentiable, so v is continuous. That's something that very many students miss when we're actually grading the AP exam. So just keep that in mind. But again, IVT problem as a nice little throwback for you. Okay, next it brings us to question C. 14C states, it is known that 10 is less than or equal to v of 13 is less than or equal to 17. Well, I look over at my table and I go, yeah, we don't have anything about v of 13. So they're giving us all the information we have. So we're given some information about the range of v of 13. It then says, find all possible values of the average rate of change of v of x on 9 to 13. So there's a couple different things I want to do here. The first thing I want to start with is I want to just write out that statement that they gave us. So they're giving us a interval with 7 that bounds v of 13. We also know that we're talking about the average rate of change here. And so again, consider this moment, I'm just kind of exploring what's here. So if we want to do the average rate of change on the interval from 9 to 13, that would be v of 13 minus v of 9 all over 13 minus 9. So that's what we're trying to eventually get to. And you'll notice, since we know all about 9, we actually have v of 13 minus v of 9, so that looks like 8, over 4 is the expression we're trying to find. So our problem is we have multiple different possible values of v of 13. So the question is kind of how do we bound this thing that's the average rate of change? Well, what I'm going to do is I'm going to attempt to mimic this expression right here. I'm going to attempt to recreate it right there. So that sounds a little weird for the moment, but I mean there are a couple different ways to do this, but that's going to be my theory. So what I'm going to do first is I'm going to recreate the numerator. So basically I want v of 13 minus 8 to be in the middle of this expression. So what I'm going to do is I'm going to take the 10 and subtract 8, and take the 17 and subtract 8. That's going to give me 2 less than or equal to v of 13 minus 8 less than or equal to 9. So what I've done is I've now bounded the numerator based on the restrictions for v of 13. That gives me the numerator. I also need the denominator. Well, that's easy enough. To get the denominator, which I'll do with a different color, because why not? To get the denominator, I just need to divide the middle by 4. And of course, if I divide the middle by 4, I have to divide all 3 sections of the inequality by 4. What that gives me then is that 1/2 is less than or equal to v of 13 minus 8 over 4, which is less than or equal to 9/4. And more importantly, that's the same thing as saying 1/2 is less than or equal to v of 13 minus v of 9 all over 13 minus 9, and that is less than or equal to 9/4. So it tells us that the average rate of change on 9 to 13 is between 1/2 and 9/4. So again, not particularly rated to differentiability, but I think it's a really important skill to be able to do, to take some interesting information and to try to find a way to, solve something else or pull some other information about a function out. So again, in there, what did I do? I wrote down what they gave us, including what the implications were for the average rate of change. I then reconstructed it using the bounding information we were provided right around here, and eventually I got my answer. So again, challenging question, particularly the first time you see it, but it shall not be the last time you see it. So hopefully this was a good first exposure. Okay, that brings us to 14D. So 14D starts by stating a new function. Let c of x equal the cube root of 8 minus v of x. And for the sake of time, I'm just going to go ahead and rewrite that as 8 minus v of x to the 1/3 power, just in case I might have to differentiate it or something. I don't know what's going to happen. So I'm going to start there. The question is c of x a differentiable function? And we're supposed to explain our reasoning. So we want to know if this thing is differentiable. So there's a couple clues. The cube root suggests the presence of a particular type of differentiability issue. In particular, it suggests that there could be a vertical tangent. But it's a little bit tough to figure out vertical tangent stuff when we have this function with 8 minus v. There's another function in there. So what I'm going to do is I'm just going to differentiate the function and see if we can look at the derivative. Because truthfully, this is almost enough. We know we're supposed to set the argument equal to 0, but let's just play along for a second. So if we want to calculate c prime of x, we need to look at this as c of u, which I think is copper in the periodic table, but I might be wrong. Maybe it's robber. And u. So I'm going to let u be the inside. That's 8 minus v of x. The outside looks like it's going to be u to the 1/3. If we take the derivative, we get 1/3 u to the negative 2/3. And of course, u prime would just be negative v prime of x. If we bring everything together, we'll get that c prime of x is, with some simplifying kind of built in, bear with me, get negative v prime of x divided by 3. It was 8 minus v of x was u to the 2/3 power. So in this case, we have negative v prime of x over 3 quantity x minus v to the 2/3 power. So what I notice is that 8 minus v of x being equal to 0 would imply that c prime is undefined. Right? You can see that too, right? Because the numerator would be a non-zero number, or even at very least we'd have a 0 in the denominator. So basically this is the condition that we have to look for. We need to see if there's ever a time where 8 minus v of x equals 0. So in other words, if we add v of x to both sides, what we're really asking you is, does 8 equal v of x anywhere? Because if v of x never equals 8, then we're fine. This will never be equal to 0. We'd be done. Well, we don't have a lot of information, but looking at our table, is there ever a place where v of x equals 8? Yeah. V of x equals 8 right there. Add x equals 9. So in this case, v of 9 equals 8. And what that tells us is that there is a vertical tangent at x equals 9. And then all the work that we already showed would be our justification. And by the way, if you were worried that maybe it was a hole or something else, notice that v prime of 9 is equal to negative 5. So we would, in fact, in this case, get 5 over 0, not 0 over 0. So if you were interested, just know that's true. So from there, we got our vertical tangent. Turns out that c is not differentiable, which again, I'm going to abbreviate diffable, at x equals 9. I should have been more specific in my explanation. But there it is. Very tough question, very challenging question, but it brought in the 1/3, all that different stuff. But keep in mind, if you'd really wanted to, you could have just started right there and just said, well, if this is going to have a non-differentiable point, since it's a cube root, that would have to be true, and you could have gotten x equals 9 that way. So just keep in mind there were multiple ways to approach it. I took the one that my mind ran with, but your mileage may vary. Okay, last but not least, and hopefully over soon. Let p of x equal kv of x squared when x is less than or equal to 3, and v of 3x plus b when x is greater than 3. Find the values of k and b such that p of x is a differentiable function. So, heck yes, we've got another differentiable function manufacturing kind of problem. We're going to try to make these values work out just right, and we even have a really good approach for this. What we're looking for in this case are two things. We want to make sure first that p is continuous, and we want to make sure second that p prime is continuous. And our hope is, in this case, we'll end up with a system of equations from these two that will allow us to solve for the values of k and b. So let's start on the left side. We want p to be continuous. So that's the easiest. Remember, we did say that there were those 3 steps, but we can focus on the one most relevant and most restrictive, let's say it that way. We want to figure out and make sure that the limit, or what would be true if the limit as x approaches 3 from the left side of p of x is equal to the limit as x approaches 3 from the right side of p of x. So we're pulling right out of the table, or right out of the piecewise. So on the left side, that's going to be kv of 3 squared. On the other side, we'd have v of 3 times 3 plus b. So simplifying a little bit, we get kv of 9. On the right side, we get v of 9 plus b. Like I said earlier, I get a lot of x equals 9 here. So v of 9 is equal to 8, so this becomes 8k. And likewise, this becomes 8 plus b. So once again, there is our first equation. Notice it's a two-variable equation. We have both k and b in there, so we can't solve it from just the first equation. There's nothing that we can do there. So that means it's time for us to move forward and check on p prime. So as with before, we do need to start by figuring out what p prime is equal to. And that's not trivial in this case. So p prime of x is going to be the derivative of each of those steps. Keep in mind, because of the x squared and the 3x, that this is going to require a lot of chain rule. In fact, each branch requires some chain rule as we go through. For the sake of time, though, I don't want to spend as much time on the chain rule portion. You can look at the written solutions. I think I did it more carefully on there. For the sake of time and space, I'm going to point out that the first one's derivative, this is going to be kv prime of x squared times the derivative of x squared, which will be 2kx v prime of x squared when x is less than 3. And then the second one, we've got v prime of 3x times the derivative of 3x, which gives us 3v prime of 3x. And then 0 for b, because that's just a constant. And that's for when x is greater than 3. So given that, we need to determine what is the limit as x approaches 3 from the left side of p prime of x, and what would it take to make that equivalent to the limit as x approaches 3 from the right side of p prime of x. So in other words, we're checking to make sure that the derivatives, left-hand and right-hand limits, come together. So in other words, we're trying to eliminate any possibility of a sharp turn. So putting in 3, we're going to get, it looks like 2k3 v prime of 3 squared on the one side. On the other, we'll have 3 v prime of 3 times 3. Simplifying a little bit, we're going to get 6k times v prime of 9. V prime of 9 is negative 5. On the other side, we're going to get 3 v prime of 9. Well, hey, we have that also as negative 5. So pulling some information together, we get negative 30k equals negative 15. And in this case, we only have one variable. We just have k. So we can divide both sides by negative 30. We're going to get that k is equal to 1/2, which is huge. That's half our problem, speaking of half. And then now that we have k equals 1/2, we can pull it up here and plug it in. We get 8 times 1/2 is equal to 8 plus b. That means 4 equals 8 plus b. And that means if we subtract 8 from both sides, that negative 4 is equal to b. And with that said, we've now found both two scalars and constants values that are required to make this function continuous. And if you wanted to go back and check, you absolutely could. I, on the other hand, have been doing this for a while and feeling a little bit sick to my stomach. So I hope this has been helpful and informative, helped clarify some of these pieces of differentiability. Kind of a small topic in the long run, but definitely one that you should be able to master and should be ready to go through. As always, I hope that this has been helpful to you, and thank you for watching. Have a great night.